So just to recall, what we've done so far is introduce this Kolmogorov complexity problem. And we've seen that average case hardness of time-bounded Kolmogorov complexity is in fact equivalent to one-way functions. And there are two directions. First, we constructed a one-way function based on time-bounded hardness of time-bounded Kolmogorov complexity, average case hardness. And then we showed that one-way functions in fact imply average case hardness of time-bounded Kolmogorov complexity. I want to highlight a few key technical insights that were made here. The first one was in the first direction. And when we constructed a one-way function, we constructed a one-way function that was length preserving. Okay. So it embedded a Kolmogorov complexity instance of length n into some one-way function instance of length n plus log n or something. And that was very important in the proof. And in the other direction, there were the following two key insights were made. So recall we wanted to prove average case hardness of time-bounded Kolmogorov complexity. The first insight was that, in fact, people have been trying to prove average case hardness by constructing PRGs. But the insight was that actually a PRG is too much. It suffices to have something called a conditional PRG. A conditional PRG is just a PRG, right, where I'm running it on a seed that comes from some arbitrary distribution. This distribution does not need to be efficiently computable. It does not have to be uniform. As long as the seed is short, that's enough. Okay, and this was actually super easy, right? It was a one-liner, and it doesn't matter which distribution I start off with. Okay, so that's the number one insight, that we don't need a full-fledged PRG. We can do something weaker. The second insight was that to prove average case hardness, as opposed to worst case or errorless average case hardness, we need something stronger in our PRG. We need something called an entropy preserving PRG, a PRG that in fact its output is dense in the output range. Okay, and that was enabled by adding this conditioning. So this condition enabled us. So by considering the weaker notion, we can also strengthen it in this other way. And those two things together was needed. But I want you to remember this thing in particular, because we're going to use that later on, that actually to prove even just errorless average case hardness, you don't need a full-fledged PRG. We need just a conditional PRG. And as a warm-up there, we saw something else. We saw that, in fact, we can construct these conditional PRGs from auxiliary input one-way functions, right? I want to make another little remark here. When we define conditional PRGs, we can define this as saying that this distribution here is picked once and for all, or you can consider a distribution that's decided as a function of the attacker. In fact, if you go back to this original little proof here, I can pick this as a function of the attacker. It still works. Like if you have some particular attacker that breaks MKTP, I can now pick this conditioning after the fact also. So that's going to be, it's not really important because you can prove that these two things are equivalent using the minimax theorem, but it's going to be easier to just remember that conditioning can be picked even as a function of the attacker. Okay, so those are the what I want you to remember. And so summarizing, using those key insights, we proved the equivalence of one-way functions and average case hardness of MKTP. Okay. Now, we proved this here on assuming average case hardness on the uniform distribution, which is good because it's a very natural, the most natural. But if I would like to use this in a constructive way, remember I said that if KT is easy, then I can do all these amazing things. Science becomes easy. Okay. Now, what this says is that if you can break this one-way function, then you can do science for random phenomena. Not so cool, right? Okay.
To be able to do a comparison for things that don't have a short.
Exactly, not so relevant. Now, so what we actually care about is, if I can break this one-way function, can I do it on other distributions also? And in fact, we can prove the following generalization, that it suffices actually that KT is hard on average on any sampleable distribution. If it is hard on average on any sampleable distribution, then in fact you also get one-way functions. Now there is a little asterisk here. This is not exactly true for KT. It's true if you consider a randomized version of conjugate complexity, where the program that is supposed to generate the string is allowed to be randomized. Or it's true for KT if you assume some randomization assumptions. I'm not going to go into detail on this, but for now, just like think of it this way. Okay. Like a corollary of this thing is something quite intriguing. What this says is that KT, if it's hard on any sampleable distribution, we have 1A functions, and if I have 1A functions, KT is hard on a uniform distribution. So we get to this problem. Hardness on any sampleable distribution implies hardness on the uniform distribution. That's a pretty curious thing. Do we know this type of result for other problems? Hardness on any distribution gives hardness on the uniform? Anyone?
Do you know?
I know it on some very awkward things. Like typically you would think that, yes, anything that's what Seth was talking about, random self-reducible things, when you have like worst case to average case reductions, and if you have worst case to uniform distribution reductions, which you would think you have for things like LWE, you should think that you would have something like that. Turns out that actually even for LWE and for lattice problems, these worst case to average case reduction don't actually show that if you can solve it on the uniform distribution, you can solve it on any matrix, because there is some additional requirements on the length of vectors. So it doesn't actually solve it always. As far as I know, the only other problems for which you know these type of things is something like discrete log, when I select the prime that I do modulus in some as not being part of the problem, right? If you do g to the x mod something like the prime being something very particular, 2 to the n-1 or something like that, in that case, we know how to re-randomize things. But even for like the discrete log mod p, we don't know how to re-randomize things. We don't know how to re-randomize p. For QR, we also don't know how to re-randomize the n.
But what about permanent?
Okay, we have re-randomizability in things that are outside of NP. Okay, they're not useful. So what I'm asking about, can we do it for things within NP? And there, I think like discrete log maybe is the only, I don't know. Maybe I'm missing something here, but when we talk about re-randomizability, I asked ChatGPT and it told me discrete log, QR, and graph isomorphism. Graph isomorphism seems nice, but again, it's the same thing. Graph isomorphism is re-randomized. We'll fix one of them. The other one you can re-randomize, but not the two. So this kind of shows a very curious thing about this problem. It actually gives you some kind of re-randomizability. If it's hard on the uniform on any distribution, it's hard on the uniform distribution. So I think it highlights like this problem. Even though at first you think there's no structure, it kind of has like a very, very meaningful property. I wouldn't call it structure, but it is something very curious that we typically only knew how to do using something like, yeah. Okay, I'm not going to really go into the proof, but like the proof, the idea here is that when we do this multiplicative argument, it actually works for any distribution that's not very far away from the uniform. And in fact, any distribution that doesn't sample things with probability more than 2 to the minus their Morgan complexity, something strange. But so any distribution that doesn't sample elements with probability larger than 2 to the minus their Morgan complexity, the proof actually works for. Okay, seems like a bizarre thing, but there is something called the coding theory in their Morgan complexity that says that you cannot sample elements with probability larger than 2 to the minus their Morgan complexity. And recently there were some more efficient versions of it that show that the same thing can be done also for time bundle Morgan complexity, at least if you allowed randomized algorithms or using the randomization. So these are the two kind of steps going to it. Okay, so now let's go back to the Holy Grail, because that's where we wanted to go, right? We wanted to base one of the functions on NP not equal to P. We have now shown these two things. One of the functions on KT are equivalent, KT being average case hard. And I said, the only thing that remains is to show how to go from worst case hardness to average case hardness, and to show that MKTP is NP-complete. So to go from here, NP not equal to P, to this. Those are two things we want to do. missing. Now let's go back to Yevgeny's question. Okay, so and let's focus on just the simplest thing. I want to go from worst case hardness to this. Can we do it? Can we go from just worst case hardness of MKTP to one functions? And indeed, this is not a new question. This is something that's been studied, not for this, but more generally. From what languages can worst case hardness imply one functions? And there's a long vein of work showing lots of barriers, and in essence saying that if you want to base one functions on the worst case hardness of some problem, this problem has to be in AM co-AM. Okay, so that's pretty bad news because MKTP is very unlikely to be in co-AM. In fact, there is something called the Rudis conjecture, and if you assume this Rudis conjecture, then it's easy to show that it's actually not in co-AM. So we don't believe this to be in co-AM. So if we take this barrier seriously, we cannot hope to do it. Okay. Now, there are two ifs here. Number one, this is only for black box barriers, and we'll see we can use non-black box techniques here. Number two, even they're not full black box barriers. Might still be possible to do a black box proof. And there are a lot of annoying limitations on this thing, and many of us have spent too much time trying to remove them. Still open to actually rule out black box things. But at this point, I'm less interested in it because we know we can get around them anyway. So, and in fact, the first thing that shows that there is a lot of hope is this breakthrough result by Hirahara from 2018 that showed that you can take worst case hardness of MKTP and get average case hardness. So you can go almost from here to here. There's just one catch. He gets errorless average case hardness. Okay. Whereas to get to one function, we need two-sided error. Okay. So this was really a breakthrough result and very surprising because it went around this barrier. And so what I was planning to do now is to actually give you a proof of Hirahara's result in one slide. Okay. So this is not exactly how he wrote it, but really, if you expand things out, this is kind of what happens anyway implicit in his proof. But this will be a kind of a more abstract view of the proof, and it will make it a lot easier. Okay, so what it shows actually is if you consider some kind of a gap version of MKTP problem, where the goal is to decide whether cosmological complexity is large or small. Okay, there is some gap in between. So that's the goal. Okay.
Sorry, sir. I just want to make sure it's triviality. No, not the statement, but the notational thing. So you at some slides you have case of P. Some slides you have case some polys.
Okay. Yes. Okay. Because this result actually, when I write poly here, I need it to be hard for all polynomial. Okay.
Oh, so it's like
and this result says if it's hard for all polynomials, in that case, you can need to do something.
Should they pay attention to this stuff?
You should ignore it for now, okay? But yes, technically, Hirahara's result requires all polynomials or for sufficiently big ones. Ignore it for now.
We don't think that's where the cheating happens. Basically, we think
there is no cheating anywhere. You mean this is a beautiful result. There is no cheating. It's but yes, maybe that is like in some sense, yes, the non-black box aspect actually comes from that. To be honest, yeah. Okay. Okay, so what I want to show is that this gap version of the problem, if you assume it's worst case hard, then in fact, it's also going to be errorless average case hard. Okay. Now, we have already learned stuff about errorless average case hardness. What have we learned? It's a quiz. It was on that slide with the light bulb. What do we need to do to get errorless average case hardness? Conditional PRG. Okay, Abhishek is right. Okay, so if you get a conditional PRG, then we have errorless average case hardness. Okay, so if we want to prove this result, the only thing we need to do is to construct a conditional PRG. So we saw already that auxiliary input one functions imply conditional PRGs. Now we want to construct a PRG, auxiliary input conditional PRG from worst case hardness of this problem. Okay? How can we do such a thing? We don't know how to construct PRGs from worst case hardness. Or do we? Anyone knows any PRGs from worst case hardness? Sorry? I know, yes, but I think you also know. Some of you know. There are two types of PRGs in this world. They're the ones that we do in crypto literature, and they are based on the hardness of inverting some one-way function. Okay? What? And there's another type called Nielsen-Wittgerson's, and they are based on the hardness of computing some function. So what does Nielsen-Wittgerson PRGs say? They say they construct something, they take some function, f, they construct some PRG based on this function, and they have the property that if you can distinguish this output of the PRG, then you're able to have a small algorithm that computes the function. Okay, so you have a small algorithm that uses this attacker to compute the function. Now, what does this actually mean? This means that if I give you, and this is actually what Nielsen-Wittgenstein can do, they start off with a function that's hard to compute, hard to compress. They say if you start off with a function that's hard to compress, you plug it in there, that's going to give you a PRG, right? Because if you can distinguish, then they have an algorithm that computes it. This is a small algorithm because the reduction is something small, the attacker is something small, and that computes the function, so it compresses the function. And that's Nielsen-Wittgenstein proof, okay? This is sometimes, this kind of, the way I define the PRG here is something called a reconstructive extractor. Okay, it's something that from this, if you can distinguish, you can compute the function, so you don't need this exact construction. Any reconstructive extraction works, okay? So if I take a reconstructive extractor, in particular like Nielsen-Wittgenstein, and plug in something that's incompressible, it's indistinguishable. All right, but we don't have that something that's incompressible. What we want is something that is a reduction that takes some instance, and I want to be able to decide it. Right? Now, I have this problem that's worst case hard. What does it mean that it's worst case hard? That means that for every attacker, there exists some input he makes a mistake on. Okay, so there exists some input. For every attacker, there exists something that has small cohomology complexity that he thinks has large cohomology complexity, right? And in particular, this gap, I have something that's like very, very tiny, but the attacker thinks it has large cohomology complexity. If I just take that thing, such a thing exists, right? If I take that thing and I consider the Nielsen-Wittgenstein PRG, when I plug in that input to it, what will happen? It's going to be indistinguishable with respect to that attacker. So for every attacker, I have some function that can mess him up. And this function is small. So I have some string with small time-bounded cohomology complexity that will mess him up. I claim that's going to give me a conditional PRG. What is a conditional PRG? It's just, sample a small program, use that program in the Nielsen-Wittgenstein. Conditional on event that what I sampled was the right thing for that guy, it's indistinguishable. And that's it.
How does Nielsen-Wittgenstein build the PRG from this program?
Nielsen-Wittgenstein builds a PRG from any hard function.
Yeah, but
so I just take my small program, I run it to get a string, which I view as a function, and then just run Nielsen-Wittgenstein on that function.
Oh, as an input.
No, that is like Nielsen-Wittgenstein is parameterized by a function, right? So the function that I'm using is just the output of the program. So I take a small program as my seed, I run it, I get a truth table.
You apply the construction.
I apply the Nielsen-Wittgenstein construction using
the
truth table as that's it. So Nielsen-Wittgenstein use it using actually something that's hard to compute, or you could use something random. I'm here, I'm just saying, I'm going to use it in something that's not. Okay, it's probably not, but I'm using the input, an input on which he thinks it's is incompressible, and therefore it will be hard to distinguish.
So in the conditional PRG, the conditioning can be adversary dependent?
Yes. So you missed that, you came late. Yes. So the conditioning, this conditioning being adversary dependent or not is actually not a thing. Like to prove this, it's enough. That was enough in the previous proof. But you can also go from one that is adversary dependent using minimax. So it's actually not an issue. But you don't need it. It's like really very, the proof is like, as I said, 3 lines like that.
So for Nielsen-Wittgenstein, you need average case hardness of F, and you're saying
no, okay, yes, true. Nisan-Wittgenstein, yes, but there's IW there. So if you use like a better, that's what reconstructive extractors are, like something you can reconstruct the whole thing. The original Nisan-Wittgenstein was like that average case, but if you look at the IW ones, it's actually for worst case hardness. So it's something that computes the whole thing. And really, it's like in this setting, you can do much easier. You can just apply any array recurring code. You don't need it to be locally decodable. It's even easier here, but yeah. All good? So the key insight here really is that these conditional PRGs are enough, and they are actually really easy to build using Nisan-Wittgenstein. And then we get this breakthrough result that overcomes the barriers. Note that this is non-black box. Why is it non-black box? Because the way, in fact, in this thing, the compression happens, first of all, the conditioning was adversary dependent. And really what happens is like I'm actually using the attacker in order to do the compression. If you look at what goes on, if you trace everything back. Okay, so good. So we've gone from here to here. We're going from here to here. We just have this annoying gap between errorless and hardened average, which is kind of, maybe a tiny gap. Like it was never clear whether these two notions are different or not. Seems that this tiny gap is maybe not so easy to do.
But just to check, so in this tiny gap, you went to the only problems that you defined, KT. So previously there was 1,000 letters, here you're back to K.
Okay, no, because this is, I wanted a nice picture. The other letters, min KT, okay, is just, it's called the MKTP is the decisional version. What can I do?
So there is a...
No, this is the decisional version, is good enough, right? In fact, there was this whole discussion decision to search. Implicitly, also, we show the decisional search on average traction equivalent. Also, let me not go into it. There's a lot of other things that are known to. Now, so really, you want to go from here to here. The only gap you need to bridge is this. So if you're complexity theory, then I would ask you to look at this. If you are a cryptographer who loves PRGs, we now know that this is equivalent to conditional PRGs. This is equivalent to conditional anti-preserving PRGs. So, can you just go from conditional PRGs to conditional anti-preserving PRGs? Then you're also done, okay? IFTAC doesn't think that's possible, but who knows?
So entropy preserving is precise. It's like no entropy loss. Just exactly.
Well, log n bits entropy loss.
So PRG is stronger than a con PRG.
PRG is stronger because a con PRG is a PRG with the seed comes from any distribution you want. Just short.
Not necessarily entropy preserving.
Exactly.
So can you go from PRG to cond PRG?
Yes, that we showed, right? Because from PRGs we have one-way functions. From one-way functions we constructed it. Yeah.
Is there some similar picture for one-way because for one-way permutation?
Nothing is known. It's a great question.
The non-black box adversary was the non-black box use of the adversary wasn't going from
Nisan-Wittgenstein is non-black box.
yes, so that wasn't going from worst case to average case hardness.
Yeah.
But isn't there a black box barrier also going from average case hardness to one-way functions? Or?
Not complete, but yes. Like so far, we'll get to more things. Okay. I wanted to, yeah.
Are auxiliary input one-way functions equivalent?
Well, we're gonna get there. Okay, it's a very good question. Okay. Are auxiliary input one-way functions equivalent to one-way functions? Still great open question. We're gonna now bounce around a little bit on that also now, actually. Okay.
Black box barriers to the last thing that we have,
To which one?
to the question mark.
This thing?
Yeah.
Well, we've already used non-black box techniques. So, no, so that's black box barriers. I don't know exactly. And it's not so relevant. Maybe it's a fun exercise, but like,
Or non-black box.
I don't know. Yeah. Yeah, it's a good point. Okay, I'm going to give you another thing that's equivalent to this now. Okay, that's more curious. That's more related to some of the other things we saw before. Can we construct zero knowledge for NP? Can we construct zero knowledge for MKTP? Turns out getting zero knowledge for MKTP is equivalent to this also. Curious phenomena. Okay, let's do it. Okay, so to do that, we need to do a little detour and discuss this question of does zero knowledge exist and is zero knowledge equivalent to one-way function? So what is known with respect to this question? Does non-trivial zero knowledge imply one-way function? We typically say yes, of course they do. Okay, well, it's a little bit subtle what's known about this. And this original work by Ostrovsky and Widersen that showed non-trivial zero knowledge, what's called non-trivial zero knowledge implied one-way functions, it shows the following. They show two results. The first result says that if there exists some language in zero knowledge that's worst case hard, then you don't actually get the one-way function, you get an auxiliary input one-way function. And then I have a second result showing that if zero knowledge is average case hard, in that case you get a real one-way function. Okay, is it clear? Worst case hardness gave you auxiliary input one-way functions. Average case hardness gave you all the way. Now it's a little bit not exactly clear what they proved and what they stated. They stated it as like this. It says average BPP. Average BPP means errorless average case hardness. But in the proof, in the definition, it seems like they only did the actual like average case hardness with two-sided error. But one little tweak of the proof, one extra line actually gives what they claimed also. Okay, so this is the current scenario. We don't know if non-trivial zero knowledge actually implies really one-way functions. Now there was a breakthrough last year on this by Hirohara and Namashima also that showed that actually you can bridge this gap. Okay, and you can actually get the real one-way functions by just assuming that zero knowledge contains something that's worst case hard. If you additionally assume that there exists zero knowledge for all of MP. So if you have zero knowledge for all of MP, and there exists something that is average worst case hard, then you can get 20 functions. Their result actually was only for like P/poly, but we'll see now a proof, a slight strengthening from our paper that also works in a uniform setting. Okay, so if you look at it in the right way, this whole thing is going to be very simple, and it's going to give you a stronger result. In fact, even stronger than this, it's going to be the following. It will suffice is that not only you have zero knowledge for all of MP, it's enough that you have zero knowledge for MKTP. Okay, so if you have zero knowledge for MKTP, which is inside NP, right? Then worst case hardness of zero knowledge implies one-way functions. Let's prove it here. Okay, does anyone already see the proof?
No, we didn't show it yet.
Okay, so let me see it. Okay, it's going to be fit in here even under one line being used for assumption. So let's assume that zero knowledge is non-trivial, and let's assume where we have a zero knowledge proof MKTP, number one. All right, what does this mean? Zero knowledge is non-trivial. We're going to just do like pattern matching here. Zero knowledge is non-trivial. OW says we get auxiliary input one-way functions. Okay, click. So now we have auxiliary input one-way functions. Okay, we would love to use this. Okay, if you can use this, we're done. Can we use this somehow? What have we learned today about auxiliary input one-way functions? Conditional PRGs, right? Auxiliary input one-way functions imply conditional PRGs. And what do conditional PRGs do? Average case hardness of MKTP, all right? Great. So auxiliary input one-way functions give conditional PRGs. Conditional PRGs give you, and remember this was a triviality, right? Give you average case hardness. Okay, now we have average case hardness of MKTP. But if we have zero knowledge from MKTP, then we have something in zero knowledge that is average case hard. And we're done. Boom. Okay, any questions? So as a direct corollary, this is a weaker statement. We get that if MKTP is worst case hard and MKTP is in zero knowledge, then we also get one-way function, right? Because if MKTP is in zero knowledge and MKTP is worst case hard, then there exists something in zero knowledge at worst case hard. And that's exactly this, that if you assume that you have zero knowledge from MKTP, okay, if you assume that KT is worst case hard, then you therefore get a one-way function. So assuming this, you can go from here to here. Now the other direction is trivial because if MKTP is either MKTP is easy. If it's easy, there's a trivial zero knowledge proof, just send the witness. Okay, and if it's hard, then we have one-way functions. And if you have one-way functions, then you do GMW. Boom. There's a little star here because this doesn't really work on all input lengths, but on some input lengths it's but except for that, it's a real equivalence. It's a stupid direction that doesn't work for all input lengths, but. All right, so now we've learned that, this is a kind of deep question. It's related to something about PRGs. It's related to worst case every case reduction, and related to constructing zero knowledge from MKTP. Now you might say, look, we've constructed a bunch of zero knowledge for lots of cool languages, right? In particular, statistical distance and lots of very nice languages. Why not do it for this? There are some issues with this, right? Remember, I said MKTP is not likely not to be an AMCOM. And SDK, we know, is an AMCOM. So not likely to be able to use the techniques that we currently have to construct it. But it doesn't mean it's impossible. We might still be able to construct something unconditional for this. So I think it's actually, to be honest, this is actually the direction that we're currently looking at, because this is a very tangible approach, a constructive approach to constructing this reduction, just construct a zero knowledge proof. Okay, so that's that's one approach to just directly go from.
Should be statistical zero knowledge in some sense because you assume nothing. I mean, can it like?
I don't assume nothing because I can assume worst case hardness of this. And that is powerful because I have conditional PRGs. So it's not nothing. It's a lot actually. They're very indistinguishable. They satisfy a lot of things. Okay, so that's one direction. Another direction that's been taking on in the last year is to say, if we can't do it based on the exact worst case hardness of this problem, let's consider some friends of it, some variant of it. Okay. And indeed, there's been a few different results with Yanni and a different result by Harana Mashima. So in the upcoming crypto, we have the following, which I think is a kind of clean version of MKTP. It says the following: let's not look at the full problem, but let's look at a promise version called a boundary version of the problem. Okay, so what's a boundary version of a problem? Again, this is not exactly true. It only holds for the probabilistic version unconditionally, or for exact one if you have the randomization. But let's ignore this point for now. Okay. In the original MKTP problem, okay, the task is to distinguish whether cohomology complexity is big or small. Let's fix some particular threshold being n-1. So the question is it super big, truly random, more than n-1, or less than n-1? Okay. And one can consider, in fact, goes back since the 80s, a generalization when you have two different running times. So when it's in the smaller one, the program should be small and with small running time, but to show it's big, it's not only big, but it's also big even if I run polynomially longer. Okay, so that's kind of a gap version where there is a gap in the running time. This goes back to Co from the 80s. Okay, so this is the MKTP. And now the boundary version is to say the following. I don't need it to be hard always. I want hardness to appear somewhere that's close to the threshold. So I'm going to only look at instances that cohomology complexity is somewhat large. So the cohomology complexity is always more than n-log n. And your goal is to distinguish, is it more than n-1 or less than n-1? So in this regime, I'm restricting to instances with large cohomology complexity. In those guys, can you decide between n-1 and bigger or smaller n-1? And that's the what we call the boundary MKTP problem. And it turns out this problem is actually worst case hardness for this problem suffices. Now, the curious aspect of this problem is that you can consider boundary versions of lots of different other problems, like SAT. Boundary SAT, I tell you, here's the SAT formula. It's either fully satisfiable or 99% satisfiable. Is it worst case, does worst case hardness of this imply normal hardness of SAT? Yes, no? Yes, those things are equivalent. Almost every other boundary problem that you look at, hardness along the boundary implies worst case hardness all throughout. And there's a good reason for it. In fact, you would clearly think that you're supposed to decide something is big or small. If I give you what are the hardest instances, it's exactly on the border, right? That's what should be the hardest intuitively. It's not always trivial to prove it, but for many problems, actually, this is super fun. You can play around with it for SAT. For SAT, it's a very easy one. For 3-SAT, it's a little bit harder to do the reduction. But basically, any problem you think of, except longest path, that one we don't know if it's equivalent or not. And it seems like it's not. shortest path it should be, but for longest path, not clear. Okay, but everything else, there's some really cute little reductions for proving that hardness on the boundary is the same as normal hardness. For this guy, we don't know. If you could prove that it's equivalent, hardness on the boundary is equivalent to normal hardness, then you would have done it. Okay, but in any case, the result is boundary hardness, worst case hardness of this problem actually suffices. Again, I'm not going to go into it on at all, but the idea of the proof, and this again is a non-black box technique here, that says the following. Let's look at the construction from before. This construction, the attacker, you have an attacker that breaks the money function. He's going to succeed in doing the deciding KT, but there is a small fraction of instances on which he can fail. Since it's a small set of instances on which he can fail, those instances themselves must have small Kolmogorov complexity, right? Because there's only a small number of them, so you can enumerate them, so they cannot be too complicated. And therefore, in fact, they can also be efficiently compressed using using this coding theorem and so on. So therefore, those instances on which that algorithm will fail actually fall outside of the promise. So on the promise, I'm always going to succeed. Okay, so the picture now overall looks the following. ONA functions, average case hardness is equivalent. It can be uniform or any sampleable distribution, in fact, right? We can go from errorless to worst case. This is a gap, or alternatively, we can get a characterization in the worst case using boundary. This is just a glimpse of results. There's been lots and lots of other results, lots of other characterizations and so on. I'm not going to go into it at all. And again, this is a biased sample, but hopefully a good biased sample. Okay, so that was all I wanted to talk about in the first section. Like this was the biggest. Now these are going to be two much smaller ones. Okay. So the second thing we're going to look at now is the computational complexity of this problem. Okay, this has nothing to do with crypto a priori. Okay, but we'll see that actually crypto will be very important. Okay, so the first one is this Perebor conjecture. Remember, I said that since the 60s, it was a conjecture this problem, solving KT, has no non-trivial algorithm. Last year, with Noam and independently Hara, Ilango, and Williams, actually provided the first attack on this problem, the Perebor, the MKTP problem. This attack is not, or it's not an attack, it's an algorithm, or I don't know if we call it an algorithm because it's a non-uniform algorithm. Okay, so it's a circuit that solves this this problem, but it's a non-trivial circuit. It's less than size 2 to the n. Okay, so it breaks the kind of non-uniform Perebor conjecture. Now, I don't think they actually, in the 60s, discussed the distinction between, at least in Tractor and Brod's essay, there's no distinction between uniform or non-uniform. I think what they meant was the uniform version, that there's no non-trivial algorithm. So I think what they called Perebor is still kind of open, but it's still very natural to think about, does there exist a non-trivial circuit for this problem? And no such circuit existed. Okay.
Does it follow from Fiat no or heuristic or heuristic gap?
It's going to follow basically directly, yeah. So as Evgeny guessed, the way this works is that we have constructed a one-way function from such that if you invert this one-way function, then you can compute Kolmogorov complexity. So the only thing you need to do is to break this one-way function. Right? We know how to break one-way functions because there are these generic algorithms, time-space trade-offs, that show that there are non-trivial RAM programs that invert any one-way function. Okay, this goes back to work by Hellman, and I don't have time to go over the algorithm now. The Hellman's algorithm is very simple and beautiful, and this was extended to a much less simple algorithm by Fiat and Orr, and they show that there are non-trivial attacks on any one-way function. This requires a big pre-processing, and then big running time, but it's still sub 2 to the n, so non-trivial.
The pre-processing is preparing the circuit.
Now, this is a little bit trickier. They did not do it as a circuit, in fact. And to really curious, Ayush gave a talk, and it's exactly the same issue. In fact, we rediscovered what they did 2 years earlier. So you need to take this one and redo it into a circuit. Can you take the Fiat-Nor algorithm and write it as a circuit? And the problem is exactly the same problem as what they have. Yes, maybe the running time is small and the amount of memory you have is small, but you make many queries and implement a circuit, it blows up into a circuit that's going to be non-trivial. But if you use exactly what they did that we didn't know, and use these sorting circuits in basically exactly the same way, you can implement it as a circuit. Now you have to mess around a little bit because this algorithm is something that took 2 to the 2/3 n. Okay, and the way we do it, we lose. Okay, and so we get on to something that's 2 to the 4/5 n. This shouldn't be the right number. Okay, you should at least be able to go down to 2 to 2/3 n. Maybe if Ayush looks at it, we can, maybe you guys did it better. But it is what it is now. Okay, and so basically by just using this algorithm, writing it as a circuit and doing it in the correct way, you can invert the one-way function and therefore break this problem. It's quite intriguing that the idea of developing crypto, like both this thing and this thing, is useful for actually solving this problem, and we still don't know all. It's only been a year, but there's no other way to do it that we know except doing to this. It's quite. And I don't know, is this the first win-win where we, like, the other thing was a win? Where usually we think of win-win as like, we can't break it, so we're happy because our crypto works. But here, actually, we're happier that we could break it. And
so how much do you think you can push this? I mean, could you get to a little of n?
Like, even Fiat-Nor should be really n/2, right? That's the lower bounds are n/2. We cannot hope to push this better than n/2, and but we still have a gap towards Fiat-Nor, even.
Where does the non-uniform advice come from?
It's the way. Now I didn't want to do it, but the way the Hellman works. Let's say I have a permutation, okay, and let's for simplicity say this permutation is really like a circle, okay. So if you apply this function, you go around in this cycle like this. What Hellman does is I'm going to store a bunch of these like special points here, okay, and that's we're going to store non-uniformly. Whenever I get my input that I would like to invert, say I want more. Let's say my input is here. I'm going to go and apply the function f and start walking around here until I find a special point. When I have a special point, in my list of special points, I'm actually going to store a back pointer. So if I get a back pointer, I jump back to somewhere like this, and then I start walking forward again until I get to the guy that came right before him. So I just need to store square root n points to be able to just walk 2 square root n steps, or square root n steps, actually. So that gives you 2 to the n/2. That should be the right bound, but one loses some to do it when it's not like a circuit cycle.
So some could you're saying high levels that there is a difficulty going from RAM to circuits, and that's why you need to this machinery.
Yeah. No, they're not the machinery from this. No, that RAM to circuits is really, yeah, it's kind of curious that we missed it, and those guys also independently did it. They also had missed their paper, but I guess it's, I should read all IO papers. Is the conclusion. Yeah.
Is there a way to do things directly on RAMs, so the problems will be uninteresting?
No, then it becomes easier. Yeah, but it's like nobody defined Perebor on RAMs. Yeah.
Would it be interesting? It seems like, I mean,
yeah, no. If you do it on RAMs, you get 2/3, 2 to 2/3.
No, but just the whole equivalence, maybe like circuits is the wrong model because of stupidities like that. Maybe it's like, would it be interesting for your big program to just forget about circuits?
No, we don't do circuits. We do Turing machines all throughout. This is just, hardness.
Oh, this is like I see independent.
Yeah. Now, let me point out here that the key thing that's important here too, again, is a length preserving property of this function. Otherwise, you could do this on SAT too. So that's why I'm saying construct a length preserving thing from SAT is really awesome. Because if you do that, you break SAT. Sorry? Just plug it in here, yeah. If you construct a length preserving one from SAT, then you have broken a strong exponential hypothesis.
If you have done what now?
If you can find a length preserving worst case one-way function from SAT, like the one we do in homeworks is like multiplies by 2. And if you do multiply by 2 here, it's not good. It's more than n. That's the only issue, okay? So it doesn't have to be even super length preserving, just, you know, yeah. So I don't know, might be possible, right? Okay, second hardness. Second hardness is it NP complete, right? And that, as I said, is a question goes back to the 60s. And lots of recent work has shown, in fact, towards what Levin tried to do. And it's shown that lots of very nice variants of MKTP actually are NP complete. So there are lots of friends of this notion, okay? Oracle versions of MCSP or conditional cohomology complexity even. Lots of things that look very similar, okay? But not this one. There are also a bunch of works that show barriers, okay? But they're quite limited. They are either Oracle separations, which we know we can overcome for there are lots of barriers that are, and they are with respect to deterministic reductions and variance theorem. Deterministic reductions, they're still very nice works, but on a high level, it's very easy to understand why deterministic reductions can never work. Anyone sees the idea? If you have a deterministic reduction, you need to take a SAT formula, and your deterministic reduction needs to map it in something, okay? If it's a true instance, you need to map it in something that has large cohomology complexity. True is, needs to have small cohomology complexity. And if it's a false, it needs to have large cohomology complexity, okay? How can a deterministic thing do this? The description length is small, so you cannot extend the cohomology complexity of things. So you can just, like, if you have reduction, just answer everything with no. And that means that you're able to solve SAT on anything that has small cohomology complexity, right? And so, of course, it can break all PRGs and whatever you want. So therefore, this cannot be possible assuming one-way functions. Now, that's, of course, we don't use random, we would expect to use randomized reductions. So, so this question is quite intriguing, because even if we think it's not NP complete, the only way we typically know of proving that something cannot be NP complete is this co-AM barrier. And this thing is not in co-AM, so we cannot use that barrier. So it's a very beautiful question just for that reason. Now, if we assume IO, it is NP complete in a non-black box way. And that goes back to all the results saying that if you have IO, if NP is worst case hard, then you have one-way functions. Okay? In fact, now using what we saw earlier, you can even prove a stronger result than that, which is that if witness encryption exists, worst case hardness implies one-way functions. And why is this true? Well, because what we saw was if zero knowledge is worst case hard, we have one-way functions, but witness encryption implies zero knowledge. So using this previous result from a few slides, witness encryption implies zero knowledge for MP, and that implies one-way functions from what we saw.
Now, do you have a simple direct proof? Do you think this can be turned into a simple direct proof for just this downstream implication?
Which one? This one?
No, just this last thing. This witness encryption implies. Witness.
This is a proof of that, right?
No, sorry. I meant no for this assuming witness encryption and the middle line.
Yeah, this one. Yeah, so that.
Do you think there's a nice direct
without OW?
Yeah.
Well, it depends if you do like.
Sorry, without what?
Like, so the way we've seen today was now I'm saying, hey, I'm giving a proof with this encryption that gives us zero knowledge. And we saw using Ostrovsky-Wittgenstein, we had a simple proof using Ostrovsky-Wittgenstein as a black box. I don't know. Yeah. Might be that one could even do it. Yeah. But actually going from here to here was like, since that paper, we actually wrote that explicitly as an open problem to go to witness encryption. We knew how to do it average case witness encryption. And so for over like, whatever it is, 10 years, it was open to just do this result. So
Yeah, no, this is very cool. That's why I was wondering if
there's a direct one, yeah. So now it's like, you know, it's much, and this was actually pretty, I think, hard to prove. It wasn't an easy paper, even it was the first version that was printed was even wrong because it was pretty complicated. It was like obfuscation and obfuscation. And so now one can do this in a much cleaner way. Now, so why is this result relevant? Well, it means that we have some, assuming witness encryption, MKTP is non-black box NP-complete. Why? Because if you have worst case hardness, you get one-way functions, and one-way functions imply hardness of this. Right? So if SAT is hard, then MKTP is hard. So in a non-black box way, it is NP-complete, assuming witness encryption. Okay. So witness encryption says it's non-black box NP-complete. Okay. Now, if we take Amit's heuristic, that if you can do it with encryption, it's true, then, sorry, it just means that, you know, this is what a non-black box means. NP being worst case hard is equivalent to MKTP being worst case hard. That's kind of like, what does NP-completeness mean? It means that these problems are as hard in polynomially. So that's what it means. If this is worst case hard, then this is worst case hard, and that's equivalent. So that's true, assuming witness encryption.
But you don't get an actual reduction. Like not
No, this doesn't give an actual reduction. Yeah.
You wanted to again, there is a different letter. It's not KT.
No. That's my fault. It should be up there. Yeah. Here, I'm not. In this talk, I'm using the same problem all throughout. In other talks, there are lots of variants, friends of this thing, but I'm using only one here in this whole talk. That's why I said.
It's why if NP-completeness, like longest pass, shortest pass, you change like one parameter.
No. I'm not. It's same problem always. Yeah. This is like totally clean. Okay. Now, so this is kind of some bizarre notion of non-black box NP-completeness. Okay. But if you want to do actual NP-completeness, what's the answer? We don't really know. Okay.
I didn't follow what you mean non-black box.
Okay, so maybe there was it means that they're like MP is worse.
Active, you mean non-black?
Non-constructing, yeah, non-constructing. Basically, it says MP is hard if and only if MKTP is hard.
Okay.
Yeah, those two problems are equivalent with respect to P. Okay. Now, what does normal NP-completeness mean? It means there are two ways that we typically define it: using corp reductions or using something called Levin reduction. Corp reductions means I can map X from a SAT to this instance of NKTP, okay, such that this is true if and only this is true. Okay, this is in SAT if and only if this is MKTP. And there is something called Levin NP-completeness. This is how Levin actually defined NP-completeness. Now, in textbooks, when we teach complexity theory and so on, people stick with this thing because Corp did all these reductions this way. Okay, but as cryptographers, we actually always need Levin's notion. So what is Levin's notion? It's something also called witness-preserving NP-completeness reduction. It's something where I take my instance and a witness, and I can map it to a new instance and a new witness for this thing. So given if I have a witness, I can get a witness for this thing. So think of in zero knowledge, right? I would like to prove a zero knowledge for SAT. We reduce it to graphic coloring. But it's important that from my SAT formula, I can also get a coloring, because otherwise the proof we can't do stuff. Okay?
But is it important that there's a way to go back?
Yes, and then the second way is like, now you also need to go back in Levin's definition, that if I have a witness for this thing, then I should be able to get a witness for the original thing. It is important, right? Because typically how you prove sumness, the proof of knowledge property says if I do this, I want to go back and get a witness in the original thing.
What about Turing versions of all these things?
You can do Turing versions. Turing versions is like, it's not a good way to define NP-completeness because,
Sure,
yeah.
I'm just saying with regard to MKTP.
Yeah, you could, and we don't know much about it, yeah. Okay. And this is, as I said, this is often what we need. In particular, this backward direction is often we use for soundness. We get some witness here, we'd like to get a witness for the underlying thing. So in a recent result with Noam, we showed that if you have I/O, then MKTP is not Levin NP-complete. I/O and sub-exponential one-way functions also.
Meaning under deterministic reduction?
No, anyone. This is actually a complete, there is no Levin reductions at all, assuming I am. Okay? I don't have much time, but I'm going to do this in 2 minutes because I'm not going to do the actual proof, but I'm going to give you the insights. Okay? This is not how the paper is written, but there's a new paper with Noam and a student, Tomer, that explains it in this other way. And so here is the idea. Okay? And to explain this thing, I'm going to go through a new cryptographic notion. Okay? And I hope that you agree that this is a very natural notion. Something we call witness pseudo-canonicalization. What is witness pseudo-canonicalization? It is something where I give you some MP statement, X, and a witness, and the question is, can you take this witness and map it into some canonical witness? But it doesn't have to be fully canonical, it's just pseudo-canonical. Okay? What does pseudo-canonical mean? Well, any two witnesses should, the pseudo-canonical witness should be indistinguishable. Okay? Interesting question. You know, we can also do it for promise problems. Let me not go into that. Okay?
For example, if you could do a random witness, that would be a canonical?
If you can get it to a random witness, yes. A random witness for a statement, right?
Yes, for X.
Yeah. Okay.
Sorry, in the first case,
Uh-huh.
what's the output of
The first case just says that, you know, if I have a true witness, when I canonicalize it, it still remains a witness.
So
This is just says like the canonicalizer still keeps it a witness. And the second thing just says that it's actually pseudo-canonical. That
so but it shouldn't depend on that view. So it always up to the same one.
well, yeah, no, it's pseudo, so it's indistinguishable. So if we start with W or W prime, the distribution of the witness will be the same. Okay? Very clean notion.
Computation.
Computation indistinguishable, yeah. Observation 1. This one is closed on the Levin reductions. Right? So if you have it for one language and there's a Levin reduction to the other language, you have one for that too. Not surprising, that's why we use Levin reductions in crypto all the time, right? Because if I have zero knowledge for this thing and I have 11 reduction, I have zero knowledge for that also. Good. Okay? But that's, you know, why 11 reduction is the right notion, at least in the crypto setting, and that's also where we can rule it out. Okay, now the question is, what languages have pseudo-canonical, witness pseudo, I messed it up here. Witness pseudo, WPC. Which languages have WPC? Sorry? Oh, unique witness languages have it. It's great. It's a non-trivial notion. You can do it, right? If you have a unique witness, great. Anyone, anything else that has it? Well, yeah, we're using IO here, so MKTP has it. MKTP has WPC if IO exists. Why? So what's a witness for MKTP? It's a small program, okay? Can you take a small program and turn it into another small program? Anyone knows how to do that? Amit? Run whatever Amit did, okay? Run the IO on the program, and you get a different witness that's indistinguishable.
Don't you have the size problem? I mean,
Yes, that's why it's like, you know, that's what, when it's a promise problem, I wrote it there. It's enough that it's when you're dealing with a promise problem, you get something that's bigger, but it's enough that you have a witness for something from not no.
Yeah, okay.
Yeah. So I need to define this correctly, yeah. So assuming this thing, you have it for MKTP, MCSP, all meta complexity problems, IO is great for. It's really quite curious. Yeah. Okay, what about SAT? Does SAT have WPC? It says no. So. Anyone sees why? Let me give you a hint. Okay, hash functions. How would you define a language with hash functions that doesn't have WPC? Well, you know, just the most naive language, the language of pre-images. I give you y, a witness is a x, such as h of x equals y. Okay? If given this, a witness x, if you can canonicalize it or pseudo-canonicalize it, you're going to find another input that's another witness, which is a collision. Right? Why is it a collision? Well, because the thing that you start off with doesn't depend if I start off with this guy or this guy. So if I start with a collision, for one of them, it's going to work. Yeah. Sorry? So, okay, why SAT? Because I said it works for language of collisions, but can you reduce the language of collisions to hash function SAT? Yes, you can just, you can just view this language h of y equals x as a SAT. So if you have witness canonicalization for SAT, you can also use it in order to canonicalize preimages to a hash function. If you can canonicalize preimages to a hash function, then you can find collisions very easily. Just sample x and f of x or h of x, and then try to canonicalize the preimage in a random way. And that's it. So SAT cannot have witness canonicalizers. No, we're in clauses. SAT is NP-complete. So sorry? It was of all NP-complete languages. Yeah. Any NP-complete language, because you can write, the language h of x. This is, it not even have to be SAT. It has to be language of collisions. But of course, like.
You usually need one-way functions. It's like worst case one-way function.
Okay, so now you ask, like, why the hell do I need these one-way functions? Okay, because we know that if I have I/O, I can go from NP equal to P to the already, right? So, and indeed, like, there are two versions of this result. If you want to deal with Levin reductions that are something that people call honest, that is polynomially preserving, in that case, it's fine. Okay, you don't need when it functions worst case is enough. But if you want to deal also with reductions that maybe send something very small, then I cannot do this because I'm going to once I canonicalize it, maybe that's going to break the. It's not longer going to be secure with respect to attacker because it's such a small input length. So in that case, you need to do some kind of like either I can brute force it, or so to deal with non-honest reductions. This is the problem that appears in many contexts where you have these two scenarios, whatever. But it's not interesting, right? The interesting thing here is like there's a different barrier now to non-NP-completeness, and that barrier is understanding what languages, just as we used SDK as a barrier before. Like languages that have SDK are unlikely to be NP-complete. And here's a different one. Let's look at languages that have WPC. Assuming I/O, meta-complexity has WPC. There might be more languages WPC. I think it's a quite interesting notion to look at.
Can you go back to the definition now that we have more?
It's a very simple definition. WPC is just like take your witness and apply your WPC to it, you get another witness. And the second one
is efficient.
And it's efficient, yeah. Okay, so good. So we have now ruled this out. So one way to interpret this is that either I/O does not exist, then we don't know anything, or if I/O exists, then it's not NP-complete. Now you can interpret it in two ways. One way is that I/O exists and this is not NP-complete. And another way is to say, Kolmogorov was not a stupid guy, and Levin wasn't either, and they believe it was NP-complete. They worked very hard on it. So maybe this is a way to break their assumptions and get another win-win for cryptography. So, and indeed, as I said, people have been trying to prove that it's NP-complete, and they're getting closer and closer. In fact, in another paper with Lou, Noam, and Igor Oliveira, we can actually rule out, using this paradigm, we can actually rule out various different versions of I/O. In particular, something called rate 1 I/O, where you want to take your circuit, obfuscate it, but the circuit shouldn't grow by too much. Okay, we know how to get rate 1 constructions for other things, but for I/O, turns out you cannot do it. And you can also not get something I/O for database-aided circuits. Okay, so you would like to obfuscate a program that accesses some outside database. Can you obfuscate that? Turns out you cannot. Why is that? Well, the way we do it is we just rely on this thing, and combined it with known NP-completeness results. Because as I said, there are versions of MKTP that are NP-complete. If you plug in those guys, then you get these results. Now, I don't know what that means. I side with Amit. I think that probably IO is more likely, but
We can get rate 2.
no, there's a difference there. Even the rate 2 is this. I need rate 1 in the circuit size.
Oh, sorry.
Yeah.
All the existing work on NP hardness of MKTP and versions and MCSP, etc., are they Levin?
Essentially, everything in the world is Levin. Okay, the PCP theorem is Levin. Essentially, anything you can think of. There is, I guess, we found what is it? Unique SATs. Unique SAT to SAT is not Levin, but people don't really view that as an NP complete. Like, you don't think that unique SAT is NP complete. So it depends how you view it. I think any like. Sorry?
Interesting randomized reduction.
Yeah, exactly. Yeah. Vazirani. That one is not 11. Okay. So how much time do I have?
Yeah.
Okay. So I'll do 5 minutes very briefly, wrap up. Okay, I'm not going to really discuss this. So as I said, there is also this key exchange. You all know what key exchange is. Two people want to interact, and then after this interaction, they should be able to reach a joint key that an attacker should not be able to learn. This is what we need for security on the internet. And for those, we only know it based on this very structural assumption, not even heuristic. Like Boss Brack said, it's kind of an endangered species, these things, because we only have like 5 assumptions in essence that imply security of these things. So we show how to base this on the hardness of a Kolmogorov complexity problem, which is an interactive generalization of Kolmogorov complexity. So very roughly speaking, and I won't go into detail now because I don't have time, in this interactive Kolmogorov complexity problem, you look at what happens when 2 people are interacting. So let's consider 2 people interacting. They generate a transcript and some output. Okay, interactive Kolmogorov complexity of the transcript and output is the shortest program for A and B that generate the transcript and output. Okay, so Kolmogorov complexity is what's the shortest program generates the output. Here I'm looking at the shortest program that generates shortest program for both A and B that generate the transcript and output. Yeah.
Both A and B are time t bounded.
Yes. Yeah. So IKT is
Same output.
here. You can consider it for the same output or different output. For key exchange, the easiest characterization is when it's the same output. Yeah. So for now, I just look at the same output. In essence, the problem, it's going to be the worst case hardness of distinguishing whether IKT is small or large. In fact, actually, it's not going to be, IKT is going to be small or Kolmogorov complexity is large. And the worst case hardness of this problem turns out to actually characterize key exchange. And the protocol, let me just give you a minute what it is. It's kind of crazy. The protocol is the following. I pick a random program, random length. You pick a random program, random length. Then we talk, blah, 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 blah. We talk for a while. At some point, we generate some output. Okay. Now, we don't know if we're going to have the same output at all. Probably not. So then we do an equality check protocol. So I send a hash of my output, and you send a hash of your output. We check if you got the same thing. If you got the same thing, great, we're done. If we didn't, go back. Okay. That turns out to work. Sorry?
How long is the output?
Whatever it is, it's going to be of length t, roughly, yeah.
Why would it be time efficient?
They run in time t only. You let them talk up until t, where if you define IKT.
But you said if not doesn't work, repeat.
Okay, so then we're going to repeat it n times. Yeah.
But why would it work in n times?
It will. Yeah. Okay, so and the final thing I wanted to mention is that in a recent year or so, we've been trying to see whether we can get something practical out of this also. We're pretty far from it. But kind of the current simplest barrier is to say, can I get a practical PRG? That seems to be the first non-trivial primitive. Then we're kind of hopeful to try to get something that's practical. We know we can get PRGs from only functions, right? So it's not, we could just build a function and construct a PRG using, but that's going to have n to the cube overhead. Not great.
Sorry, so okay, just going back. The reason it'll work is because by the Levin type of thing, you'll happen to guess the actual key exchange protocol.
No,
And run it.
no, it's not. Yeah.
It's not the reason.
Yeah.
Okay.
Yeah, no, because I'm going to reduce to this assumption. It's going to be something that reduces it to the assumption. Yeah. Okay, so we've been trying to build a practical PRG from this thing, and so last year with Yanni we did have a direct construction of a PRG, so it doesn't pass through one function, so just directly from the hardness of this problem, a direct PRG. Okay, of course, there's we could have gone.
If you manage to do a one-word permutation, this would be solved, right?
Yes, but we don't know.
It's open.
It's open. Permutation is great. Yeah, I'll mention too. Okay, so we have a direct PRG construction like this. Yanni also actually has now been working on implementing it. It's not great. It's not horrible. It takes like 0.1 second to run, which probably is pretty bad given that like Elaine managed to do like ORAM in milliseconds, but but at least it's a starting point. It runs on the laptop at least, okay?
Why do you measure it in seconds and not in like number?
I don't know. That's what he did. I didn't implement it because we're not in operations.
You can say any number. It would be informative.
Yes. No, like the point here is that it outputs something on the laptop. Okay. But the cool thing is like if you can push it to be faster, is that there is a really nice way to set security parameters to these type of problems, because we're basing security on the hardness of a pretty natural problem, which is compression. And compression is actually, it's not just us who care about it. Amazon cares about it, and if they can do better compression, they will make a lot of money. Okay, so it's not just the hackers. And really, the hardness of this function is based on like some very particular thing, like pick a random Turing machine of length, something, run it, and can you compress the output of this? Okay, so can you compress the output of a random Turing machine? And we can check on which security parameter this becomes secure by running state-of-the-art compression algorithms. Okay, so it's quite nice, and so you can have this like very simple challenge problem. And there are other challenge problems like this. There's something called the Hutter price, which is to like compress Wikipedia. This is very related. I can give you something, and here's a problem of saying, how can you compress this to, half the size or whatever it is, even much less. Yeah.
Sorry, is K 1,000 or is it a parameter?
K is 1,000. Yeah. Okay. And the cool thing is that up until recently, he was trying as a generic attack gzip. But in the last few months, something really awesome has happened, that the best algorithms for compression are, surprise, surprise, LLMs, okay? Because they are starting to take over many algorithmic problems. So
larger than Wikipedia, no? So it doesn't make sense.
It does still make sense. It still makes sense because the LLM compresses it. Like I will get out the compression, it's going to be small eventually. Okay, I'll tell you later. Actually, it's related to your how you did things with non-compressing distributions, because you can look, this LLM, basically you try to get the LLM to predict this thing, and then you just look at the probabilities it's doing, and you can compress those guys. So it's actually very nice how they do it.
I'm saying the LLM might contain
the LLM, no, the LLM is a big non-uniform algorithm, but eventually it outputs a small compression.
But like,
sorry, you're right, yeah.
Isn't it trivial to compress if you have non-uniform advice bigger than the string you're compressing?
No, the non-uniform advice is independent of the instance. So I'm fixing some big non-uniform advice, still not trivial to compress.
Not Wikipedia, compresses everything. This is what we say.
Yes, it's well, yeah, exactly, yeah. So
if it only compresses Wikipedia.
No. I agreed with you that the Wikipedia challenge is somewhat questionable. Okay. So those benchmark, but like this is a better benchmark, okay, because it's harder to cheat on this thing. So it's quite cool that kind of this problem is aligned with. In fact, there is this like idea now that maybe the right way to evaluate LLMs is if they're actually, how intelligent they are, is based on how much they compress. That's a very clean way to like say how smart you are. And so
Maybe I'm confused. What if I replace M by AES? Is anything you say changes? So what does the setup do?
Because if you compress AES, it's true, you would break it as a random oracle, but you wouldn't break it as a, like, that doesn't give you a break on the PRG.
No, AES of 1 on a secret key or something like that. I'm trying to see, I'm losing the connection. This slide is nice, it doesn't have any weird letters, so I don't see what it is.
Okay, so what I'm saying is that the construction has the property that if you're able to distinguish this PRG from uniform, then you do get an algorithm for compression, right? Or compression of something, okay? The reductions, it compresses this particular, it breaks this compression problem.
This is access, I can do the same with AES. I run AES of 1.
Yes, you can plug in AES here, and that probably is going to be, look, you could, instead of this thing, you could plug in AES into our construction, and that will give you something based on the, it will give you something where if you distinguish the output of our PRG, then you're able to compress the outputs of AES.
With AES to get one function.
Yeah, you could use AES to get a PRG, yes, with approval reduction, which is probably fine too.
The thing is, you're compressing output of random programs as opposed.
Yeah, but I can compress AES also if you want. It doesn't matter what I start off with. All right, so the conclusion is we've kind of introduced this and explained how to use this new pillar. More complex, there's lots of cool things happening. And I hope that all of you will be interested in continuing this kind of work. Thank you. And obviously, huge thanks to Yanni and Noam, based on which most of these works are together with either one or the other or both. Thanks.
Is there? I mean,